Combinational network. So what is that? Logic network constructed of AND gates, OR gates, and inverters are also called combinational networks. Combinational networks have several features of note. So one, input or output lines are not tied together. So for example, the output it's not a loop. It's not connected with the input. Line can be split like this one here. I split the line. 3, there are no loops, as I said, where the output of an element is part of the input of the same element. And finally, the output of the network is an instantaneous function of the input. So whatever input, right away you get some output. There are no delay elements that capture and remember input signals. So in the middle there is no memory. Goes from here and output is here. Notice also that the picture of any network is in effect a directed graph. So for example, the network is given. Let's write the expression and also the truth function. So again, the expression for this network is as follows. Here, x1, x1 naught, x2 plus x3 naught. And here is the truth table for it. Here is another example where we have to deal with exclusive OR. So first it says write the truth function for the Boolean expression. We did this in the previous video. And the next question, it says draw the logic network for this exclusive OR, and we've seen it before. And here is the network for based on this definition right here. So what I have is x, y naught, and then x naught, y, and then OR between them. So x, y naught or x naught, y. And now this logic network is given, but the question is show that this network represents x exclusive for or y. So as you see, they are different. They look different, but do they represent the exact definition of the exclusive OR based on the input x and y? It says recall that bitwise exclusive OR operation is used in DES, and DES stand for Data Encryption Standard. And most of the time now, most computers, and we use mostly AES because some people, this one is breakable. DES is not as strong encryption standard as AES, which is Advanced Encryption Standard. This on the side. If you read chapter 5, it's talk more about encryption and decryption. But let's go back to this question. The question is, are these two networks the same? For the same input, do we get the same output? So what is the expression for this network? So right here I have an OR, so I have x plus OR, and here I have xy, but then I invert it, and here the output is x plus y, xy naught. So the question is, are these two expressions equivalent? Because they both represent exclusive OR, x exclusive OR y. So are these two equivalent? So we could use truth table to prove these two are equivalent, or we could use propositional logic to show that these two are equivalent. Please stop the video and try this yourself. So right here, equivalent Boolean expression. So where we know two Boolean expressions are equivalent if they have the same truth function, as we've seen earlier. So this expression here, for example, are equivalent. So this all big one and this one are equivalent Boolean expression because they share the same truth table. So how can we prove that this one is the same as this one? Let's use some of the Boolean algebra properties to prove that. So what I want you to do is to have your flashcard with all the properties next to you. Please try this. So again, I have to go from this to this, the lot minimized. The good thing is in chapter 8.3, the good thing is that section 8.3 show you some cool method of minimizing these expressions. So right here we're going to use properties, and so what I see, if I group them and I copy this one twice because x or x is just x, so I use idempotent, copy it twice, because what I want to do, I want to start using first 1b commutative, and then I'm going to use 3b where I need to combine them. So right here I first switch this by using commutative law here and here. So this way I could kind of what we say in normal algebra, you factor, but we use distribution here. You pulled out x1, x3, x1, x2 naught, x1 naught, x2 naught. And this way what's left with is x2, x2 naught, x3, x3 naught, and another x3, x3 naught. Well, x2, x2 naught is just a 1, and here as well is 1, and here as well. So right here, x2, x2 naught is 1, x3, x3 naught is 1, and x3, x3 naught is 1. What I used right here is 5a. And now this is anything, that one is the identity, is 4b. So what I'm going to end up with is x1, x3, x1, x2 naught, and x1 naught, x2 naught. Few more steps here we need. What we need is I could pull out x2 naught. But first let's use the commutative law. And then 3b allows me to take x2 naught out, and then I end up with x1, x1 naught, which indeed is going to be 1. So here is x1, x3. And now next thing is, this is 5a, and 4b again lead me to x2 naught plus x1, x3, or x1, x3 plus x2 naught, which is the last expression I needed. So this is a little bit tedious, longer, it required a lot of writing. But as I said again, chapter or section 8.3 will show us a cool method of minimizing these expressions.